Yeah, and to my friend, to Eugenia, thank you for starting the recording. I was going to start that after we reviewed the question, but there's a very high likelihood that I would forget. So thank you for starting that for me. All right, I'm going to leave the question open in case you haven't had a chance to type in your answers yet. Let me pull up for you our responses. Let's see what we're thinking about troponin. Yeah, so when we talk about troponin, this is one of our regulatory proteins. So remember that troponin is the push pin that holds tropomyosin in place. And I need tropomyosin to block those myosin binding sites on actin. If I don't have tropomyosin, myosin is always going to be attached to actin. And I like how we see on here, we're always going to have contractions, or we're never going to be able to relax, because troponin and tropomyosin block the process of muscle contraction when we don't want to contract. So quick reminder for us of the two kinds of proteins we have inside muscle cells. Ones like troponin or tropomyosin that are regulatory proteins, and then the ones like actin and myosin that are the actual proteins. Awesome. All right, so let me review with you really fast some of the stuff that we did at the very end of our class on Monday. We were diving into the idea of excitation-contraction coupling. So we're going to explore more today the fact that a message from a neuron is going to help this muscle fiber to actually contract for us. So the way that we get a message to a muscle fiber, to a muscle cell, is we spit out these neurotransmitters, these little chemicals. Those chemicals, in particular, when neurons talk to muscle, are acetylcholine. Acetylcholine goes down, it attaches to those chemically gated sodium channels. And remember, in class, we talked about how a gated channel doesn't always open unless we have the right key. And in this case, that key is a chemical. When I open up this chemically gated channel, remember that sodium is what actually moves. So the process of opening up a chemically gated sodium channel is going to result in sodium pouring into my cell. And remember that the way that sodium exists when it's floating around in our body is Na+. It's a cation with a positive charge. So once we open up those channels, in comes the positive charge, leading us to do the process of muscle contraction. So the very last thing that we were talking about as we were like halfway out the door was the idea that when sodium comes inside the cell, it's going to cause the membrane charge to change. And that change happens not just at the neuromuscular junction where the neuron actually talks to the muscle, but also that's going to go all along the surface of a muscle fiber. So for us to make an action potential, remember potential means charge, action means moving. For me to make that action potential, I'm going to have to use voltage-gated channels. Remember, voltage-gated channels also not open all the time, but they open when the charge is wrong, and I get the charge wrong by using these chemically gated channels that I find at the neuromuscular junction. So remember, when we talked about the way that neurons work, we also had action potentials, meaning I changed the membrane charge at that part called the axon hillock. I made it positive, which then made the voltage-gated channels next door open up and make this positive, which makes the voltage-gated channels next door open up and make this part positive. What we're looking at is a moving action potential, change in charge. Oh, excuse me. So the first kind of channel to open, we've already talked about, are the voltage-gated sodium channels. When they open up, we're doing depolarization. Remember that depolarizing means that my charge goes up. Hey, here's a note I want to give you about muscle cells because they're a little bit different than neurons. When we talked about neurons, does anyone happen to remember what their normal resting membrane potential was? What was the normal charge on a neuron? Do we remember? I know it's mean for me to make you type, but thank you to all of you who are humoring me there. You're exactly right. The normal charge on a neuron is -70. So inside a neuron is more negative, 70 more negative than outside. On a muscle, I want you to write down somewhere for yourself, muscles are actually -90. They are even more negative than neurons are, -90 millivolts. So when I'm talking about opening a voltage gated sodium channel, I'm starting at -90 and I'm rushing in a whole bunch of sodium. I am depolarizing the membrane. I'm making it more positive. And because we've made it more positive, that's going to cause my neighboring voltage gated sodium channels to open up, which is going to cause more depolarization. So all the way across the sarcolemma, the plasma membrane of the muscle cell, every part of that membrane is going up. It starts at -90, in comes the sodium, and I shoot back up. But just like we saw in neurons, muscle fibers don't want to stay positive forever. So we're going to repolarize the neuron or get it back to its normal charge using voltage gated potassium channels. Again, we're back to that salty banana cell. So when sodium moves, it wants to come in. When potassium moves, it wants to go out. And potassium goes out to bring the charge back down. Sodium comes in to depolarize, to make the charge go higher. Now, those structures that we briefly talked about when we were talking about muscle fiber anatomy, they were called T-tubules. And I told you that T-tubules were places where the sarcolemma, the plasma membrane of a muscle cell, folds down inside that muscle. This is why a T-tubule is important. So I've got my action potential up here going all along my sarcolemma. Voltage gated sodium opens, sodium opens, sodium opens. I get to a T-tubule and I need that change in charge, that positive, to go down into my muscle fiber, my muscle cell. Because remember, inside the muscle cell, I've got a ton of these protein tubes called myofibrils. So I need all of the myofibrils to get this action potential for the charge to get to them. That's why these T-tubules exist. So all along the T-tubules, we keep this action potential moving. We go positive, 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 until we get to these things that are called voltage sensitive proteins. Now, a voltage sensitive protein is not quite a channel, but it's something that if I change the charge, that's going to change its shape. So in the case of a voltage sensitive protein, what happens when it changes its shape is it presses on my calcium release channels. So when I press on these channels that I find embedded in that organelle called the sarcoplasmic reticulum, I press on these channels, I open them up, and out goes my calcium. It dumps inside my muscle fiber. And if you remember from our discussion about our regulatory proteins, that calcium is what I need for to deactivate my push pin, to make troponin pop out of place. And once troponin pops out of place, tropomyosin is going to slide away. And now I can do the process of muscle contraction. So my action potential, my change in membrane charge, has to not only be on the sarcolemma on the outside, it needs to go all the way down into those T-tubules so that every part of my muscle fiber releases calcium. So let's look big picture at what we've just talked about with excitation-contraction coupling. Excitation-contraction coupling starts with excitation. It starts with a message. I want you to underline, highlight, star, motor neuron. Motor neuron. So it all starts with a motor neuron saying, hey, muscle cell, I need you to contract. The way the motor neuron talks, let's underline, highlight, star, acetylcholine. Acetylcholine. That's these little chemicals that the motor neuron is going to spit out. They're going to go down and attach to these chemically gated sodium channels that we see down here. And when we attach to those channels, the membrane charge starts to go up. And it goes up and up along the sarcolemma, all the way across the sarcolemma until we get down to those T tubules. And once we're in the T tubule, now I press on a voltage sensitive protein, which changes the shape of my calcium channel. Out comes all of that calcium that then is going to go down to troponin, to my push pin, and attach to it. Pop that push pin out, move that spaghetti noodle, and make those myosin binding sites, the places where myosin can attach, makes them now available. So excitation-contraction coupling. We started with this contraction part. That's where the cross-bridge cycle is. And today we worked our way backwards. We did the excitation part. I want to pause for a moment and give you a chance to put these steps of muscle contraction in order. Now, I want to help you with this because it looks really scary up front, all of these big technical words. But let me help you out with this. When we're talking about excitation-contraction coupling, we always have to start with the nervous system. The first thing that happens when I do excitation-contraction coupling, number one, my neuron has to spit out acetylcholine. When I spit out that acetylcholine, it's going to attach to some channels. What kind of channels does acetylcholine attach to? Do you remember? What kind of ion does it move, or how do I get them open, this acetylcholine stuff? Yeah, Ashley's mentioning, yep, and Elva's mentioning in there, Brianna for us, awesome. Acetylcholine is a type of chemical. It's going to attach to a chemically gated channel, and in particular, it's a chemically gated sodium channel. So step two, first, I spit out a chemical message, acetylcholine. Then that message went down to my sodium channels, and it caused my sodium channels to open up. When my sodium channels open up, that's going to make my membrane charge go up. And my word for charge going up is depolarize. So depolarize means my membrane charge goes up. That's what happens when sodium rushes inside. As that membrane charge from beginning to end, as I do let me see if I can write it, action potential. Ooh, that looked good for a moment, and then it died. As I move to that membrane charge all the way down into my T tubules, now I'm going to bump into my calcium channels. Those calcium channels get pushed open, and when I push them open, they release their calcium. Now that I've spit out that calcium, I'm getting real close to the cross-bridge cycle. So my calcium that I just spit out attaches to my push pin, troponin. Oh, I got someone with a mic on. Do me a favor. If it's you, go ahead and turn it off for me. So calcium is going to bind to the troponin. Push pin pops out. When the push pin pops out, the spaghetti noodle moves out of the way as well. And when that spaghetti noodle moves out of the way, now I can do the cross-bridge cycle.
10.
Help me out. I got somebody with a mic on. Let me see. Here we go. I can mute all. That'll work. Okay. So from beginning to end, what we've talked about is my neuron releasing a message. Come back. My neuron releases a message. That message is going to change my charge. That charge leads to calcium release. Ultimately, it's that calcium that helps me to get to the cross bridge cycle. Excitation, contraction, coupling. Let's try. You're good, Monica. I got you turned off. Let's try a couple of square cap questions about this. So for anyone who is missing the code, I know we've been pretty good in the chat about getting that to our neighbors, but if you were missing the code again, here it is in the bottom. I want you to tell me how acetylcholine helps with contraction. And I want to know, we'll just do the T tubules. So multiple choice question, what's the job of acetylcholine? And then a quick short response, how would you describe why T tubules are important? What's their job? We'll take a moment. A lot of us are getting our answers in. That's perfect. And hey, since we're in a virtual class, when you've answered both of those questions, feel free to send in another emoji. There's our little carrot, right? Like to motivate us. So feel free to send me an emoji or a GIF when you've answered both of those questions. If you're still working, you're good. I'm not gonna close them just yet. I'm sending in a little love for all my friends who are working on these questions. I love that, Haley. My kids just recently got into Zootopia, so I feel that GIF. It's my fave. All right, one last call on that first question. And I'm going to leave the second question open for us because I know it's hard to type and do virtual class and all kinds of stuff going on. All right, my first question asks about acetylcholine and exactly how it causes muscles to contract. And it's really important for me that you know what the job of each of the parts are when we do muscle contraction. Remember that acetylcholine is my message that I spit out from my motor neurons. When I'm talking about what acetylcholine does for me, my options are either it goes inside a muscle fiber or it opens a gate. That's part one. And then number two, what does it do in that process of contraction? When we look at what we picked, we mostly picked correctly here. So acetylcholine does not go inside. Most of us recognized acetylcholine never goes into a muscle fiber. It's going to attach to some kind of chemically gated channel. In this case, Acetylcholine attaches to the chemically gated sodium channel. When it attaches to that sodium channel, it makes that change in charge that goes all across the membrane. It's this action potential that's going to help me open up my gate for calcium, but acetylcholine itself doesn't actually help me with the calcium. It just makes that action potential that gets me there. So correct answer here, we're opening up a sodium channel and we're building that action potential. The other question that I asked you, and again, I'm not going to close this one because I know some of us are still typing in, but I asked you about the T-tubules. Those T-tubules are places where I folded in my sarcolemma. So I love that my two biggest words right here are action potential, because that's really the goal of T-tubules, the action to make the action potential get all the way down around those myofibrils. Once that action potential gets down to the sarcoplasmic reticulum, then we can release that calcium. So this is the way my T-tubules are the way that I get the process of muscle contraction to happen everywhere and not just by the surface of my muscle cell. Let me pause for a moment and give us a chance. Do we have any questions we want to ask before we move on? I'll mention, by the way, at the top of your screen, you have a little place that says you can react. So I'm going to send you some love. Dr. Ellis just sent some love. Feel free to react as you see fit during our class today. Got some thumbs up. Awesome. Yeah, and if anyone has a question, feel free to put that in the chat for me. I'll do my best to watch for those kinds of things. I want to talk with you now about how we relax our muscles after we've done contraction. So we have the regulatory proteins that make it so that contraction's not always happening. The process of relaxation is going to happen as I get that calcium away from troponin. So once a muscle contraction is done, we actually start to bring that calcium back into the sarcoplasmic reticulum. But to do that, we have to use ATP. So getting a muscle to relax involves energy, ironically. So we're doing contraction as we have calcium out of the sarcoplasmic reticulum, the process of muscle contraction occurs. When I steal that calcium and put it back inside, my push pin and my spaghetti noodle, all of that goes in place. So we pull away the calcium. This gets troponin back to normal. This gets tropomyosin back to normal. We can no longer do the process of contraction. So we are constantly in this balance of doing contraction or not doing contraction. When we're contracting, my sarcomere gets shorter. Remember, the actin and myosin slide past each other. When we're not contracting, the sarcomere gets longer. The size of it increases. So relaxation, what I want you to know about it, this is when I pull my calcium back in to the sarcoplasmic reticulum, and this process is going to take me energy. This, by the way, is the second reason that rigor mortis happens. Remember from class, we were talking about how our muscle fibers get stuck, attached to each other. The other reason we can't get them to relax is because I have no way to steal back that calcium. So myosin and actin are attached to each other, and also troponin is always out of shape. So two things that contribute to rigor mortis. When we do muscle contraction, we're usually not just talking to one muscle cell. So what we're going to talk about now are things called motor units. And motor units are when we use more than one muscle cell to contract at the same time. So maybe it's 3 muscle fibers, maybe it's 20 muscle fibers. However many fibers all get their same message from the same neuron, we call them as a group a motor unit. So when we talk about motor units, groups of muscle fibers that contract at the same time, If you're doing something major like standing up or sitting down or waving your arm in the air, that's always going to involve more than one motor unit because we have so many different muscle cells that are being involved. If you look over at my picture here, this is the picture that we started with when we were talking about a skeletal muscle, and then we've got a fascicle, a group of muscles in here. Notice that inside this fascicle, I actually have two different motor units that are controlling the muscle fibers inside that group. So more than one motor neuron will send a message when I want to activate this fascicle. And more than likely, each of my other fascicles around here are made up of multiple motor units as well. So motor units, all of the muscle fibers controlled by one neuron. When we do muscle contraction, like I said, more than one motor unit are going to be activated, but there are different kinds of contractions that we do. So we need to start with this idea of something called muscle tone. All day, every day, at any point in time, you always have a low level of contraction occurring. Part of this is to help maintain your body temperature, and part of this is just to stabilize you. Now, that general muscle tone, this low level of contraction, gets your muscles ready to do a bigger contraction. So to do an actual movement, we need muscle tone to be able to later contract. There are two ways that we contract. Way number one is called isotonic. And once you've written the word, it leads to movement. I need you to underline, highlight, star, movement. Anytime we do an isotonic contraction, movement is going to occur. There's two ways for that movement to occur. Way number one that the movement occurs is when we are shortening a muscle. So when a muscle is shortening, think about my textbook example over here. As I pull this textbook up, as my biceps muscle is getting smaller, I'm generating force, or I'm contracting to pull that book up. That is a concentric isotonic contraction. My muscle is getting shorter, concentric, and we're causing movement in this process, isotonic. We can also, though, do what are called eccentric contractions. We still see movements, but this is when I have a force that's kind of slowing down a movement. So if you took that textbook and now instead of pulling it up, now we're slowly lowering it down, the muscle fibers themselves are slowly stretching longer, but the force that's making it so that that book doesn't just drop right away, that's an eccentric isotonic contraction. So important idea here. Anytime you see isotonic, we're doing some kind of movement. If that movement makes a muscle smaller, it's a concentric movement. If that movement makes a muscle longer, it's an eccentric movement. But sometimes when you do a muscle contraction, we don't actually move at all. So this is what we call an isometric contraction. The example we see here, holding a textbook out in front of you, or every gym teacher's favorite punishment when you have to do a wall sit. A wall sit is an isometric contraction. A muscle is staying contracted, but it's not getting shorter or longer in this process of contraction. So if we're not moving, if we're holding steady, isometric. If we are moving, we have to look at which direction we're moving. We'll do a couple questions in a moment, but I'll mention we need to be able to explain what happens in concentric and eccentric contractions, how they're different. When we're doing any of those kinds of contractions, whether we are moving or not moving, we always start with, or we always use a cycle called a twitch. So when we do muscle contraction, each part of your muscle will undergo a twitch. We get a single message, and this muscle goes through the process of contracting and relaxing. So there's three parts to a muscle contraction. Part one is when we're first sending that message to our muscle fiber. So this is when excitation-contraction coupling happens. Neuron spits out a neurotransmitter that causes calcium to be released, troponin, tropomyosin moving. That's the beginning of a twitch. That's called the latent period because no contraction yet. Then we enter the period of contraction, and the period of contraction is when we start to do the cross bridge cycle. So any kind of movement that's happening during a contraction is going to happen in this period of contraction, because this is when actin and myosin are pulling past each other. But by far the longest period of time that a muscle twitch will go through is the period of relaxation. And the period of relaxation is caused by calcium. Let's underline, highlight, star, calcium. The period of relaxation occurs as I slowly use that ATP to pull the calcium back into the sarcoplasmic reticulum. As I get rid of the calcium, I can't make cross bridges anymore. And if I can't make cross bridges, I can't do a muscle twitch. For my friend having issues, at the top of your screen, there's a thing that says view. Click on view, and then I believe there's an option for view content or content focus. Hopefully that gets you back there. When we do muscle contraction, we can have a single muscle, or we can do what's called summation. And this summation is exactly the same as the summation that we did with neurons, meaning I've got more than one message before I got back to normal. So in a single twitch, we get one message, then we go back through that period of relaxation to normal. In wave summation, we've gotten one message. As we're starting to get back down to normal, we get another message. Notice that muscle contraction is even stronger. My tension is going up. But something that's special in muscle cells is they can do a special type of summation that's called tetanus. And when we talk about doing tetanus, this is caused by signals that are kind of close together and repeated. Notice that as I keep getting signals, my contraction gets stronger and stronger as I kind of move up. We have two types of increasing our muscle strength. The first is called unfused tetanus. And when we're experiencing unfused tetanus, notice that there is a period where the muscle starts to relax, but then it continues to contract and starts and stops and starts and stops. When we do fused tetanus, there's no period of time where we actually get to relax. So fused tetanus is a muscle contraction that starts and is completely solid for a really long time because there's no period of relaxation. So when you're considering these different ways that muscles add together messages, summation is normal. We get a couple of messages, increases my tension. Unfused tetanus, caused by lots of messages that are kind of spaced out, we do still get to relax a little bit. Fused tetanus, so fast messages, we never get to relax. These are the different ways that we cause muscle fibers to contract. If we want a really strong contraction, we've talked about the first way to make those muscle contractions be stronger. So the first way is to send more messages. This is what we did in summation. This is what we did in tetanus, fused tetanus or unfused. The more messages I send to a muscle, the stronger it contracts. But I can also do a stronger muscle contraction if more than one group of muscle fibers are contracting, or if the muscle fibers that I picked to contract are really big, meaning they have lots of myofibrils. The more myofibrils I have, the stronger my protein connection would be. And the final way to make a muscle contraction a lot stronger is to use very large motor units, meaning lots and lots of myofibrils, or lots of muscle fibers that are all responding at the same time. So when we do a squat, we're kind of relying on all of these different forces to lift those weights back up. We use large motor units in the legs with muscle cells that are really big, lots of different motor units at the same time. And as we go up and down, oops, excuse me, we're sending lots of messages to those muscles. The last thing I want to chat with you about are the kinds of muscle fibers or the kinds of muscle cells that I can use to do different kinds of movements. Each of these types of muscle fibers are going to be better or worse at different processes. So their names are fast glycolytic, fast oxidative, or slow oxidative. The names of these muscle fibers tell me a whole lot about them. So as you're studying these types of muscle fibers, keep that in mind. When we do muscle contraction, unsurprisingly, we've got to use energy. So the name of these types of muscle fibers tells me two things about the energy. The first thing that it's going to tell me about is how I use my ATP. So the way that I chop it up, and also how I build my ATP. Where did it come from? So when I look back at these names that don't mean a lot to us yet, notice that we have the option of fast or slow. This tells me, are you using your ATP very quickly or very slowly? That's the first part of their name. The second part of their name tells me how they build their ATP, either using glycolysis or using oxidative phosphorylation. That's something that happens inside mitochondria. So we're going to go through and break these different types of muscle tissue down one by one, but I want you to keep in mind their names tell you everything you need to know about them. How quick do they use their ATP? How did they build their ATP? So let's start with that first part of the name, the fast or the slow part. The fast or the slow part is based on the activity of ATPase. And I want you to underline, highlight, star that. ATPase. Anytime you see this ending part ase, we're always talking about an enzyme. ATPase is an enzyme that chops up ATP. The more quickly I chop up my ATP, the more I'm going to run out of it. So a fast ATPase releases a lot of energy very fast. And here's a note that I want you to write by releases energy quickly. I want you to write right up here in this space, strong contraction. Strong contraction. The faster I chop up ATP, the stronger the contraction I can do. At the same time, though, if I'm chopping up my ATP really fast, I'm going to run out of it really fast as well. So really strong contractions have a fast ATPase. Slow ATPases then are going to release their energy more slowly. So the note we should make next to more slowly, this is going to be a weaker contraction. I'm not releasing energy quite as quickly. It's more weak. But also, by using the ATP more slowly, this is going to increase my endurance. I'm going to hold on to that ATP for a really long time. So let's think about these ATPase enzymes, kind of like the two lumberjacks that you see here. So I've got over here on the left what might represent a fast ATPase, a professional lumberjack. And over here on the right, I've got kind of like a hobbyist lumberjack. He doesn't spend much time in the woods, but he wants to pretend like he does. So my fast ATPase over here, we give him this pile of wood and he's like, sweet, I got this. I'll chop it up in like 3 chops. And now you can build a fire really quickly and you're warm. Meanwhile, my slow ATPase friend over here, he's going to take his sweet time to slowly chop through this wood. As he slowly chops it for you, you're going to start to get some firewood, but it's going to take you a little bit longer to get access to that firewood. Granted, it's going to last you a little bit longer because we're chopping it more slowly. So the first part of the names in my muscle fibers, fast or slow, tells me, do you make a strong contraction because you're fast or a weak contraction because you're slow? It also tells me, are you going to run out of ATP or are you going to have it for a while? That's the same kind of information that we can get when we look at the second word in these muscle names. So the second word for some of my muscle fibers is called glycolytic. When we do have a glycolytic muscle fiber, it's getting its energy from a process called glycolysis. And all I need you to know about glycolysis is that this is the process we use to chop up glucose. In particular, the kind of glucose that your muscle cells store to do glycolysis with is something called glycogen. So glycogen, I want you to underline, highlight, star, is stored. It's inside your muscle fibers. It's already there. All I have to do is chop up the glycogen, and then I can chop it into glucose, and I'm good. Think of this kind of like from our lumberjack analogy, that pile of firewood. I've already got wood there to throw into my fire. I can chop it and I can use it really fast. But here's the caveat. When this pile of firewood is gone, I don't have any more firewood. And if that's the case, I'm going to run out of energy really quickly. So that's going to bring us to our second way of making energy, and that's using the electron transport chain, or something called oxidative phosphorylation. When we use the electron transport chain to build ATP, we make a lot. This makes basically an unlimited supply of ATP. But for us to be able to do this process, we have to have oxygen. And once you've written the word oxygen, underline, highlight, star it. For me to be able to use the electron transport chain, gotta have oxygen. If I don't have oxygen, this is a no-go. I can't use it. But if I have oxygen, the other thing we're going to underline, highlight, star is a lot of ATP. Like I said, it's basically an unlimited supply of ATP. So think of this as instead of having just a pile of firewood, you've got a whole forest full of trees. It's going to take you longer to chop down a tree and to process a tree. But once you've done that, you make a ton of firewood to build your fire. That's gonna last you a lot longer than if you have this little pile. So when we talk about our muscle fibers, if they can use the electron transport chain, they're oxidative. If they can only use glycolysis, they're glycolytic. Remember though, glycolytic, we've already got stored energy. We just have to get to it fast. It takes me a little bit longer to do the electron transport chain, but in the end, I get a lot more ATP back from it. So here's my types of muscle fibers that we see here. And to make it a little bit easier for us to do this together, I'm going to put some numbers on here for us so that I'm not going to make you type all of these long names. When I look at each of these statements over here on the left, this is how I want you to consider these different types of muscle tissue, how I want you to be able to describe them. So let's start with the first half of my statement here on my first statement. It says, I contract quickly. So if I'm doing quick contractions, this is not a trick question. Am I going to be fast or slow? If I contract quickly, just that first part of its name. Is that fast or slow? A quick contraction. Exactly. A few of you trust me that I'm not playing a trick on you. This first part here for quickly, that's going to be a type of fast fiber. And so notice down below it, here's another one that's going to be a fast. I contract quickly. And down below, here's I contract slowly. That's going to be a slow one. Then we look at the second half of the statement. For my top answer up here, it says that I use the electron transport chain. If I'm using the electron transport chain, there's something that I have to have in my cell to make the electron transport chain work. What did we say we had to have to be able to do the electron transport chain? What's got to be there? Exactly. Yep. The electron transport chain needs O2. It needs oxygen. So my first statement up here, I contract quickly I use the electron transport chain. We've got a fast, here's my two fast options. And because we use the electron transport chain, oxidative. A fast oxidative fiber, number two, that's what we described with that first statement. So help me out in the chat. I contract quickly and I build ATP from glycogen. Is that number one or number three? This middle statement right here, is this number one or number three? Exactly. Yeah, you know what I should have done? Since there's only one option that's slow, I probably should have started with that one. So fast, glycolytic. We use glycolysis, stored glycogen, to make our ATP. We contract quickly. Slow oxidative. I contract more slowly, and I use the electron transport chain. That's my last one up here. So when we think about these muscle fibers, we want to know slow or quick contraction. That's thing number one. And we want to know, where does your ATP come from? Electron transport chain or glycogen? There's a couple of modifications of, excuse me, of these types of muscle cells for you to be aware of. And this has to do with the protein myoglobin and with mitochondria. So let's start with myoglobin. When we're talking about myoglobin, remember that this beginning part right here, myo means muscle. Myoglobin is the same thing as hemoglobin would be inside a muscle fiber. But when we talk about hemoglobin, that's only in red blood cells. When we think of hemoglobin, this was my oxygen transport protein that I see inside the body. So hemoglobin transports oxygen. Myoglobin does the exact same thing. It's a place for me to offload oxygen to store it inside a muscle cell. So here's not a trick question for you. If myoglobin's job is to hold oxygen, what kinds of fibers, based on their name, who might have a lot of myoglobin? Who might need a lot of oxygen? Which of our four words there tells us I need a lot of oxygen? Yeah, exactly. That's a long one to type. Thank you to those of you who are typing it for me. When we talk about which kinds of muscle fibers have myoglobin, my oxygen transport protein, it's going to be both of my kinds of oxidative fibers, both oxidatives. So that's going to be both fast and slow oxidative. They're going to have a bunch of myoglobin because they need oxygen to make ATP. So here's a wink, wink, nudge, nudge for the quiz. When you're taking it, there might be more than one answer for questions like this. More than one kind of muscle fiber benefits from myoglobin. Same kind of deal when we're talking about mitochondria. Mitochondria, if you remember from AMP1, are the site where we do the electron transport chain. So thinking about the kinds of muscle fibers that did the electron transport chain to make their energy, what word do I use to describe my types of muscle fibers that use the electron transport chain? Or in other words, that have a lot of mitochondria. Who's going to have a lot of mitochondria?
Here's what I found.
Siri would like to answer that for you. Siri found something from Khan Academy about the electron transport chain and a proton gradient. I won't make you go into that. So I think Ayana caught my question, or maybe she was answering from before. When we talk about who has a lot of mitochondria, we are again talking about our oxidative muscle fibers. It's still those oxidative oxidative muscle fibers, because oxidative fibers use the electron transport chain, and the electron transport chain is in the mitochondria. So lots of mitochondria in both fast and slow oxidative fibers. Also, lots of myoglobin in fast and slow oxidative fibers. The question I didn't ask you that we could also make a guess from this, what if I said which kind of muscle fibers would benefit from extra glycogen? What was my muscle fiber word that meant I use glycogen for energy? Do we remember that word? It's finally not oxidative. Exactly. Yep, it's not a fun word to spell, but the word is glycolytic. Glycolytic. If I said, hey, I'm going to give more glycogen to a type of muscle fiber, we want it to be the type of muscle fiber that uses glycogen as its energy source. So heads up for you, when an athlete is carb loading before a big race, what they're doing is they're actually increasing the amount of glycogen that's in their muscle tissue. That glycogen will help them, for example, at the very beginning or the very end of their race to get that last final spurt of energy. So carb loading is helping out these glycolytic muscle fibers because that's how I get glycogen stored inside of them. Different types of muscle fibers help me with different things. So let me pull up 3 different Olympic athletes that we see here. We have at the top, we've got an Olympic lift, we've got tennis down in the bottom, and then we have a marathon in the top. When we're talking about these different kinds of activities, we use different kinds of muscle fibers to do these things. So notice here on the top, with this big lift, we are doing a very strong contraction, and we don't have to do it for a very long period of time. When we're thinking about these 2 descriptions here, very strong is one of my words. It's either fast or slow. What was going to give me a very strong contraction? Was that a fast or a slow ATPase that makes a really strong contraction? Who's really strong? We're thinking about our lumberjacks. Ooh, we're on the fence. So when we're thinking about fast or slow, and in terms of strong or not strong, the name fast or slow tells me how quickly do you spit out energy. The more quickly you spit out energy, the stronger your contraction would be. So if I have a very strong contraction, I needed to chop up my ATP very quickly. My first word here is going to be fast. I needed a very strong contraction. And hey, check it out next door. When we're talking about tennis, we're doing more strong muscle contractions. Again, for a strong muscle contraction to occur, I've got to have fast fibers. Fast to make those strong muscle contractions. When we talk about having a very short contraction, what this is telling me is I don't need a lot of endurance. This is something that I could use just the energy that's stored inside of me to power this movement. Since I only have to do it once and I've got to lift it up over my head and then drop it, I don't have to build ATP. I can use what's stored. So my word that means I have stored energy that I'm going to use is glycolytic. Glycolytic. Notice that a very short contraction, a not endurance contraction, is different than when we see this word right here, repeated. When I'm doing something repeatedly, or notice up here, for a very long period of time. When we start talking about doing something for a long period of time, this is when that little pile of firewood is not going to keep us warm for long enough. If we're doing a contraction for a very long period of time, we're starting to need to use that electron transport chain. We're starting to need to build a lot of ATP to last this long. So when we're talking about doing tennis and we have this repeated contraction, we're going to use our fast oxidative fibers. Fast oxidative. Because I'm doing it so many times, I need to make a lot of ATP. And because my contraction is so strong, I need to chop it up quickly. I have fast oxidative fibers. Remember next door over here with my lift, I still needed a strong contraction. It's still fast, but I'm not doing it for an extended period of time. Since I don't have to do it for an extended period of time, I'll use my stored sugar. When we think about something like a marathon, we've already established that with this very long period statement in here, we've already established it's got to be oxidative. But when we think about running a marathon, for the most part during a marathon, you don't have to do a very strong muscle contraction. You're just doing a consistent muscle contraction. So if we're doing something for a really long period of time, we're going to use a slow oxidative fiber for that. Because a slow oxidative fiber is going to have an unlimited supply of ATP, oxidative, and it's not going to burn through that ATP very fast at all. As we're considering these types of muscle fibers, I am promising you, you're going to see some questions just like this, where I give you an Olympic sport or I describe for you something that's going on. Think about how strong or how weak that contraction is, and think about how much energy we need. Is it something that's kind of like one and done? If that's the case, I can use glycolysis for it. That's going to be good enough. If I have to do it repeatedly for a long period of time, I'm going to have to do the electron transport chain. Let me show you really fast this, I'm blanking, Venn diagram. There we go. That shows us information about the types of fibers. So notice over here on the left, we've got the slow oxidative fibers. Remember that slow meant that we don't make a very strong contraction. So we've got a slow ATPase, but we're oxidative, which means we build a lot of ATP. I want you to underline, highlight, star, high fatigue resistance. High fatigue resistance. Fatigue means I ran out of ATP. Oops. If I run out of ATP, like we see over here on the right, low fatigue resistance, I run out of ATP and I'm done. I can't keep exercising. So slow oxidative fibers are good for endurance activities, whereas my fast glycolytic fibers are really good for short-term powerful things, like that big lift up and over your head and drop the weight. We don't have to do anything else with it. Fast oxidative, to some extent, is kind of the best of both worlds. So because it has that fast ATPase, it chops up ATP really quickly. And because it does aerobic respiration, because it uses the electron transport chain, it's pretty good at resisting fatigue as well. So like I said, kind of the best of both worlds, fast oxidative fibers, but benefits to those fast glycolytic, really strong contractions, benefits to slow oxidative, we can do it forever. To help us with practicing the kinds of things we're going to see on the homework, Let me go up, pull up a couple of square cap questions for you. So I've got 3 questions in here. Check. Yep, 3 questions about those types of muscle fibers. The first one, I've got 1 answer. The other 2, there is more than 1 answer. Let's see if we can answer these questions. I'm popping a GIF into the chat for all my friends who have finished. For any of you all who will be taking AMP2 with me in the fall, that GIF that I put in there for you, here's a little teaser for you. I suspect that that bodybuilder guy has extra high levels of testosterone and probably growth hormone. Those are a couple of my types of hormones that lead to muscle growth for us. So I found us a bodybuilder with lots of stuff going on there. Probably some growth hormone, some testosterone. When you finish answering, shoot me an emoji in the chat just so I know you're still with me. I'll turn my camera back on too, just so you know I'm real, just for a brief moment. It'll probably die again, but I want to say hi so you know I'm here. There we go. We might be working. I love it. Right as I got the camera on, Alicia, your your emoji came up, so it was like perfect. Like, is that really Dr. Alice or is it someone random? I love it. I love all the parties. That's great. Well, Mackenzie's falling asleep on me. Don't do it. No, I'm with you, man. This is the perfect weather for sleeping. All right, I'm getting a lot of emojis, so I'm going to bounce over. Let's start talking about our questions here. So the first question I asked you was about the kind of muscle fiber that's going to make the strongest contractions. When we're talking about the strongest contractions, there's kind of 2 things that make a contraction strong. Thing number 1 is how quickly we chop up our ATP. A fast ATPase liberates energy or makes it more possible to have energy more quickly. These are both going to be stronger contractions. But if we're trying to determine which makes the strongest of them all, my correct answer would be fast glycolytic. Fast glycolytic because I already have energy stored inside of me. I just have to literally cut it in half and I can use it. With fast oxidative fibers, they can make a ton of energy, but the problem is it takes them a little bit of time to do that. So to get into my contraction, that takes a little longer. It's a little bit less strong than fast glycolytic. So strongest kind of contractions ever, fast glycolytic. Next strongest, fast oxidative, slow oxidative, going to be the weakest of the contractions. My next question asked you, and we actually did this together, which kinds of muscle fibers had a lot of mitochondria? When we're thinking about muscle fibers with mitochondria, the word in their name that means I have mitochondria is oxidative. So fast oxidative fibers have mitochondria. Slow oxidative fibers also have lots of mitochondria. So having mitochondria specific to my oxidative fibers because they use the electron transport chain that lives inside there to do muscle contraction. The last question that I asked you was, let's say I'm going to give somebody extra myoglobin. Who's going to be happiest or who's going to benefit the most if I give them extra myoglobin? And this comes back to the purpose of myoglobin, which is to store oxygen. If I'm going to do extra myoglobin, both of my types of oxidative fibers are again going to benefit from that. Oxidative means I use oxygen to build my ATP. If you give me more myoglobin, I have more oxygen. I can build more ATP. Now that we've chatted through the questions, how do we feel? Thumbs up, thumbs down, or any questions for me that you want to put in the chat? How do we feel about muscle fibers? I can't see your entire name. I'm gonna say it wrong. Sierra Elise, because I can't see it all. I'm so sorry. But I loved that you gave me the mind blown reaction. That's perfect. Ella is terrified. I get that. Yeah, so I have a request to explain this question again. Absolutely. When we're looking at this one, we want to consider what myoglobin does, and we want to think about who that would help. So myoglobin is a protein that stores oxygen. It carries oxygen for me. If I use oxygen to make ATP, then I'm going to benefit from having more myoglobin. Both of my types of oxidative fibers need oxygen to make ATP. I should mention, I apologize, I didn't say it explicitly before. When we talk about a glycolytic fiber, this kind of muscle fiber actually doesn't use oxygen to make ATP. So this is the kind of fibers that will just kind of run in the background, regardless of whether or not there's more oxygen coming in. So glycolysis, the process they use to break stuff down, no oxygen required. It's not going to change their function in life because they don't actually use oxygen. But my two types of oxidative fibers do need that oxygen. So there's a question, wouldn't glycolytic benefit because they don't have any myoglobin? So it is true that fast glycolytic don't have, it's not they don't have any, they just have very low levels of it. It might have some kind of benefit to them, but from a sense of metabolism, they're not going to use that oxygen in metabolism as much as my types of oxidative fibers would. So on a scale of who benefits the most, it's going to be those oxidative fibers because they're directly using that oxygen in their building process. Yeah, and then I got a question related to, let's bounce back to the first one we talked about. What makes fast glycolytic fibers the strongest? What makes fast glycolytic fibers the strongest? Think back to our lumberjack analogy. Say that I am freezing cold and I need to build a campfire. Having a pile of firewood that I can chop up immediately all at once and light it all on fire. I can make a huge fire all at once. Whereas if I have a whole forest, yes, I can go through and chop those trees down one by one and process them one by one. Over time, I will make more energy, but because I have to put in some extra energy to chop down the tree and process it, it's not going to be quite as strong of a reaction. There's not as much ATP available right away at the very beginning for me to chop up. So glycolytic fibers already have all the energy right in front of them. They just have to eat it, essentially. Fast oxidative fibers have to build that energy. So they're going to be a little bit less strong of a contraction. That was a good follow-up question. Yeah, I've got a note here about us running out of time. I feel you. Let me just chat about our last couple of topics, and then I will let you go. The last couple of things I want to mention with this chapter here are the effects of certain things on your muscle. So we have something that's called the overload principle. The overload principle basically says the harder you make a muscle work, the more it's going to adapt to that. So when we're doing extreme exercise, we're training for the Olympics, for example, we will either build muscles that are larger or stronger than what we started with, or we're going to increase the fatigue resistance of our muscles. So we're going to make them use their ATP more efficiently, or we might help them build more ATP as we're overloading them, as we're pushing them farther than before. Two kinds of exercise you can do. Aerobic exercises, what we might consider an endurance exercise. This is primarily going to impact your oxidative fibers because we're doing these kinds of exercises for a longer period of time. So endurance exercises are going to increase the amount of blood that we send to our slow oxidative muscles. It's going to increase the number of mitochondria they have to make ATP. And while we're at it, we're also going to add some extra myoglobin to make sure we always have as much oxygen as we need. So aerobic exercise is going to overall make your muscle fibers stronger. It's going to increase their ability to last longer. They're more fatigue resistant. Compare that to when we do resistance exercise. So this is things like weight training. When we do weight training, we're impacting the fast glycolytic fibers instead. So when we impact fast glycolytic fibers, it's not so much that we're increasing the blood flow as much as we're increasing the size of our protein tubes, or we're increasing the size of our muscle fibers, our muscle cells, or we'll even increase the amount of stored sugar they have to make it possible for them to contract stronger. With enough weight training, we might start to even build some mitochondria inside these muscle fibers. But overall, what we're going to see is this growth in their size primarily. So weight training increases the size of muscles, whereas aerobic exercises, endurance training, increases the blood supply, the oxygen, those kinds of things. Final thing I want to chat with you about, and then I will let you go, is the effects of sex on the skeleton. So the strength, of skeletal muscles. When we talk about the potential strength of male and female skeletal muscle, male and female skeletal muscle strength has the potential to be exactly the same. So the skeletal muscle inside me as a female is the exact same kind of skeletal muscle inside my husband, a male. Differences in strength are not because of differences in skeletal muscle itself. The muscle is the same. What is different is the amount of muscle that males and females have. Males tend to have a larger amount of muscle tissue. The more muscle tissue you have, going back to those motor units that we talked about, the more you have, the stronger your contraction. And the places where skeletal muscle is distributed is different between males and females. Females tend to have a higher distribution of skeletal muscle in their lower body, where males tend to have comparatively more skeletal muscle concentrated in their upper body than females do. So this different distribution of the muscle tissue, along with the different amount of muscle tissue, this is what makes males and females' strength different. But I want to again emphasize for you, underline, highlight, star, male and female skeletal muscle tissue is exactly the same. Differences not about the tissue itself, but about how much there is or where it's found. Very last thing is aging. Let me pop up your blanks for you just so you can write them in. Oops, we'll talk about it. Just like we had osteopenia, the normal loss of bone over time, sarcopenia is the same thing with muscles. Sarcopenia is what happens to your muscles over time as you age. As you age, we lose a number of muscle fibers, but the fibers that are left behind are also a lot more small, and they lose some of their elasticity. So they're not quite as able to do the same kinds of straining exercises that they were when you were younger. This means that if we pull a muscle when we're older, It takes us a lot more time to recover. We're a lot less likely to because of the loss of elasticity, because of the shrinking of the size. So sarcopenia, what happens with aging, you can offset this with things like we talked about, with the resistance training or the endurance training. But ultimately, overall, there will be a normal loss in muscle strength with aging simply because the muscle tissue itself will decline. On that note, I will not keep you because we are a little bit past time. Thank you for coming today. No need to worry about whether you're on my magic list. There is not a magic list today. I will stick around for just a little bit if you have any questions for me. You have all the stuff for completing chapter 9 now, so make sure to work on that. I'm going to work on getting you some videos related to the joints so that if you want to start working ahead on that, you can. I did get a good question in the chat about when the next exam is. Exam number 5 is going to open up Tuesday morning, the day after we do chapter 8, and it's going to close Wednesday afternoon, or Wednesday evening, excuse me, 11:59 on Wednesday. So exam number 5, Tuesday and Wednesday of next week. Final exam, Tuesday and Wednesday of the week that follows. So the 2 exams left, Tuesday into Wednesday. I had a question about posting the recording. Yes, I will post this recording. I'm going to need it to process for me first. Once it processes for me, I'll work on getting it posted, and I'll put it in an announcement for you so you can find that. And I'll also put the testing dates in there as well. Y'all didn't tell me my camera froze. I look real terrible there. Let's end that. End that hot mess. Any other questions I can help out with? Again, thank you all for coming. I appreciate you being flexible with me. I have to be fully honest. My husband was actually the one who flew away in the flood. The rain was so bad. I was out to lunch with him, and I didn't dare walk to my car because I knew that I would get completely flooded out. And I at that point, I still thought I was going to be coming to campus. And I was like, I cannot be totally drenched. So I sacrificed my husband, and then we couldn't see to go driving. I was like, okay, this is not going to work. Let me check my chat here. Brian asked about the final exam being optional. It is not unless you want your grade to drop by 10%. So it is actually in the grade by itself. So you do need to take it. There is a study guide posted for it at the very bottom of Canvas. You will notice that it's not everything we've covered this semester. It is specific topics from each of those chapters. So look over that, study that. I suspect that you will do well on that exam because you are looking at a lot of content that you already know really well. So yes, short answer, final exam is not optional. It is part of your grade. Yeah, to your question, Tashana, about different names. Yes, sometimes they are called type 1 or type 2, type 1A, 1B. Yes, so if you learned them with those names, that's fine. You can attach the new names that we're using to those old names if that helps you with studying. But when you see them on quizzes and exams, it's going to be fast or slow, glycolytic, oxidative. Let me see. Somebody asked about one of the exercise ones. Let me see. Effects of exercise. Was it this particular one? Maybe. I'll leave this one up here. And if it's not this one, I can go back to the other one in a moment. Yeah, Maria asked about the final exam replacing the lowest exam. That is correct. So if/when, because it's pretty much across the board, the final exam is always better than some exam if you prepare well. I will replace your lowest regular exam score with that. So if you have a 75 and you get an 85 on the final exam, I'm going to tell the gradebook, ignore that 75, count this 85 twice. So yes, your lowest regular exam score will be replaced with your final exam score. And yeah, to your question, Jennifer, we do have our last regular class on Monday. And then Wednesday at our normal class time, I'll be hosting a review session. So on Monday at the end of our class, I'm going to ask what topics we want to review, and I will make us a review session that's optional, but give you a chance to ask about particular topics for that final exam. So last official class Monday, review session Wednesday, exam that next week, final exam that next week, I should say. Oh, the one before that, sorry. Right, there we go. Any other questions for me? All right, well, I am going to go ahead and turn off my mic. I will stick around in the classroom for a little bit if you want to ask me questions. Otherwise, good luck with your studying on this. And for anyone who has not taken the lab final yet, best of luck to you. Good luck with your studying on that. Kira, can you tell me, I don't have numbers on my slide, so can you tell me what that slide is related to? That'll help me out to know what I'm looking for. All right, well, I'm going to stop my recording. I'll stick around and I will see you guys next week.